Hello, everyone. My name is Sunny Agrawal, and today I'm going to be presenting my final risk presentation on AnySafe, a generalizable framework for constraint-conditioned latent safety analysis. So, in our problem setting, we deal with robots that have to deal with different safety constraints, right? We might train a robot that says, I don't want to, when I'm handling the Skittle bag, to have it fall out onto the table at all, right? I don't want any Skittles to fall on the table. And we can train it to do this, and we find that it is able to kind of accurately safeguard against this scenario. But what if we want now this same robot to pour us these Skittles into a bowl? Our robot has a very fixed definition of what failure means, and it wouldn't allow you to pour Skittles into a bowl, right? It doesn't have an understanding of context, and it's not able to flexibly adapt its safety behavior based on our new constraint of, hey, it's okay if you pour the Skittles out of the bag, just as long as they're at the bowl. So ideally, we want our policy to be able to take into account new safety constraints at test time without having to kind of retrain the safety behavior. In order to address that, we're proposing AnySafe, which is a framework for generalizable constraint-conditioned latent safety analysis. And I'll go through each part of this framework now. So first, we have world model training. Role models are this interesting concept where we can take many different pairs of observations, which are images of like these RGB images of our robot interacting with the world, and we can take actions of what the robot is doing. So these could be like joint velocities and things. So we can take different pairs of these and encode these observations into some latent space. And then given this latent and an action, start to predict what the next latent will be. And by doing that with enough of these transitions, we can start to develop what's called a world model, which allows us to have an understanding of the physics of the world, right? So we can encode an observation into the latent space, and then we can predict the next latent given an action. So once we've built the strong enough world model with some data from the robot, we can start to use this now as a simulator, right? We can take an initial latent and then we can start trying out different actions that we've never seen before, and see how that might affect the robot. It's almost as if we're kind of rolling out the robot in real life, but this is happening what we call in imagination. So it allows us to do these experimental rollouts kind of for free using reinforcement learning. So next we have flexible safety margin function. So this here is kind of how do we detect failure, right? So we're doing these great imaginative rollouts, but if I give you a latent, how do I know that it's in the fail set or not? And how do I know that depending on what I've told you is my current fail set? Right? So we are interested in learning this safety margin function, which given a certain latent z and a embedding of the constraint zc, it'll be less than zero if that z is in the fail set, and it'll be greater than zero if it's in the safe set. Primarily for us, we investigate something called metric learning, which takes these kind of labels of each image and classifies it into different classes, and then hopes to cluster images of the same class around each other. So then when we encounter a new image and we see, okay, it's kind of around other images of class three, let's say, then we can predict that it's of class three. So then if I've told you, hey, class three is failure, now we know that that image is also a failure. But other examples of this may include LLMs, VLMs, multi-class classifiers. The nice thing is that this is a generalizable framework that can work for any different environment. Next, we have reachability. So reachability is kind of the fundamental backbone behind our project. It allows us to compute what we call an unsafe set. So we have this fail set where, okay, anything inside it is determined to be failure. But the unsafe set is the region where if you enter it, you're doomed to fail no matter what you do, right? So these might be situations where you haven't fallen over yet, but you're definitely going to fall over. So not only do you want to avoid the fail set, you also want to avoid this, what we call unsafe set. So our method for computing this unsafe set and then being able to avoid it is called Hamilton-Jacobi reachability, or reachability for short. And we extend the previous reachability formulation and make it constraint conditioned, and then solve this with RL using these RL and imagination that I was talking about earlier. And then finally, once we've done all that work offline and done all that training, now we have online deployment. So user specifications are often highly variable, they're multimodal. So we want to be able to develop an interface that can take some text from a human, or can take a picture of what failure looks like, or can take a representative picture that says, okay, I've circled a region here that I don't want, or I want to be considered failure. And now we want an interface that can take all this different multimodal information and turn it into something that our value function has seen before. So that is this constraint embedding ZC. And we want to implement a threshold, right? So this threshold can be interpreted as almost how generally large do we want this failure set to be, right? If our text prompt says, okay, I don't want you to enter the entire bottom region, that's going to be different from, I don't want you to enter the bottom left corner. Once we have this constraint embedding and this threshold, then we can use it for something called runtime filtering, which says, okay, if our safety monitor has determined that you're above this threshold, then you're good to go. You're in the safe region. Uh, Feel free to like proceed as normal. So we might have a human teleoping it, or we might have some nominal policy. But as soon as you get below that threshold, now we need to take over with our safety preserving policy, which we learned in the previous step. Okay, so on to some results. So a question you might ask is, okay, there's been a lot of great work by the Meta team for learning these kind of internet scale image encoders. Have also been shown to work for world models. Can we just use the features learned by this encoder without any level of metric learning to be able to do failure detection? And what we found is no. When we give it many examples of images with the Skittles out of the bag and images with the Skittles in the bag, um, we find that the raw dyno features are not able to clearly separate between these two different classes. But with some metric learning, we're able to make a clear separation between the two. That's this bottom left graph, where it's very obvious that if two different vectors in this metric space have high cosine similarity, then they're likely of the same class. Another question you might ask is how using a metric space compares to doing some binary classifier. So the binary classifier is actually from previous work on latent reachability by Ken. And here we're looking at the Dubin's car example, which is a simple 3D example with this car that can move in 2D space. And we find that we're able to recover this unsafe set uh, at very similar accuracy to the latent safe paper. But in this case scenario, we've developed a more flexible um, definition of failure because um, our unsafe set is now conditioned upon some sort of constraint embedding and can be adjusted depending on the size that we want our constraint to be, where the previous work has to learn something has to learn this binary classifier and can't adjust that at test time. And then a natural question to ask is, can we extend this into constraint conditioning? So we actually find, yes, that this value function, I can pass any picture of the agent anywhere in the state space, and we're able to safeguard against a circular region around that agent at a very high accuracy. So that concludes my talk. Thank you so much for listening. I want to extend a thank you to my amazing collaborators, Junwon, Ken, Thomas, and Andrea. You guys have really inspired me during this project and helped me grow a lot throughout this summer. I want to also thank the amazing people at the Intent Lab. You guys have really welcomed me this summer and made my summer very fun in Pittsburgh. And I also want to extend a thank you to the risk program for accepting me and giving me this opportunity. Rachel, Dr. John Dolan, and the entire risk cohort have really made me feel at home here. All right. Thank you.